So we'll make it a quick presentation. I'll give you a quick summary of why do you need to use XL compilers on OpenPOWER. Then we'll have first-hand experience with Professor Istvan from PPU-CU in Hungary, and he will share some of his results as that he did it in association with Oxford e-learning center. So you will hear it from the expert. So first, IBM has has long experience with compilers, not only on Linux Power or OpenPOWER, but on AIX, in ZOS, etc. And our experience for those compilers go across languages, Fortran and C++. But what makes the compiler unique from XL compiler is the long history that we had developed to really get the best breed of technology, optimization technology that we have in our back end. Most importantly, I will highlight the interprocedural analysis and the profile-directed feedback optimizations, that you will not find it as mature for Power architecture as you have it in the compiler. One important thing, of course, that makes us very, very unique is the full exploitation of the hardware. We work very closely with the hardware designers for Power8, Power7, and upcoming Power9. So we know exactly how the processor is acting. In many cases, we suggest changes to the processor or new instructions that will make things go faster. So if you're really looking for somebody who knows exactly about Power, that's the XL compiler. From language standard compliance, we are compliant with all the latest and greatest for C++ and Fortran. One thing I would like to highlight, and it's very important for people working on Linux, is the fact that we are really dancing with the open source community, if you can use that expression, because the XL compiler is binary compatible with GCC. So if you compile part of the libraries or part of your application with GCC, you can easily compile the rest with XL and get the best performance. If you are migrating from another platform to Power and you're coming from GCC, all what you need just change the calling compiler command, but the options, the source file, etc. will stay the same. So migration is very smooth. Finally, these are a couple of performance tuning hints. Usually when you start, it's important to identify where are the bottlenecks that you need to tackle for your program, whether it's specific loops, specific modules, and for that you can use different tools that are available on Linux, like perf, opperf, gprof, etc. Then you can use the compiler to make you smarter by really generating optimization report to tell you, oh, I was able to optimize this loop, or I managed to find SIMD opportunity in this loop, or this loop was not able to SIMDize, and it will give you some hints how you can make it better. So you can change your source code to give more hints to the compiler, for example, aliasing information, to say these variables will never overlap. So the compiler can use this opportunity to give better performance. Typically, we suggest people start with O2, O3. If you are analytic workload or floating point workload, then O3 is good with QHOT. If you are more commercial, kind of off-the-shelf application, then it's better to use O2 or O2 IPA. In some cases, it is important to use mass libraries if you are HPC workload. And if you are really keen about accuracy, some optimizations will be more aggressive and overcome that. But there are information in the compiler or hints that it can give it information that to have its strictness in terms of floating point. Now we are at OpenPOWER Summit, and as part of that community, I'm glad to announce for the first time we will introduce a free compiler on the Linux platform. So starting this week, we announced that it will be available in June. It's a free of charge compiler. There are no limit. As many users can use it as you can. You can use it for production use. If you are really interested in service, then you need to buy the paid compiler. So with that, I would like to leave you with 3 important messages before I pass it to Professor Istvan. First, the compiler provides easy migration to OpenPOWER platform from any other platform. The other one is we know the hardware, so we provide the industry-leading performance on power processors. And last one, we provide world-class support. With that, I'll pass it to Professor Istvan.
Thank you, Shereen. Over the past year or so, I had the good fortune of working with the IBM compiler team since the very early compilers to really try to nail down high-performance computing performance on the POWER8. So I basically have a set of benchmarks, compute and bandwidth intensive that are basically common patterns in high-performance computing. And to begin with, this is basically the #1 benchmark anyone runs on a system. This is the stream benchmark that measures bandwidth to the DDR4 memory. And you can see that we have a 2-socket 1010 core machine. The maximum bandwidth we can achieve is somewhere around 300 gigabytes a second, which is pretty impressive, especially when compared to the competition. But one thing to note there actually is you really need a considerable amount of data, about 1.5 gigabytes per array, so a total of 4.5 gigabytes being streamed in from memory and then out to actually get there. And in addition to that, on POWER8 you can have up to 4 physical threads on each core. So from single-threaded mode to SMT2, 4 and 8. And the hardware can actually dynamically switch between them. But the point is, again, performance depends somewhat on how many threads you have per core. At higher SMT settings, you cannot really reach that memory bandwidth. And also, we have very nice caching. And with about, what is that, over a terabyte per second over this 2-socket machine. So we can sort of expect now that for scientific applications that are really bandwidth intensive, this is sort of the maximum we can achieve. We cannot really go beyond what this simple benchmark shows us. The other side of the coin is, of course, compute. And we have tried the ESSL library and specifically the single and double precision general matrix multiply benchmarks, and again looked at performance at different SMT settings. And we see that in single precision you get almost a teraflop per second, and in double precision about 500. And again, this is fairly similar to similar offerings from Intel. A 2 × 10 core machine, but we should note that Intel has 256-bit vectors, the POWER8 has 128-bit vector registers, but it does run at a higher clock. And again, we see that we only get this peak performance at lower SMT settings. So our first benchmark is a Black-Scholes a 1D benchmark. It's some very primitive form of a financial computation. And we evaluate simple scalar code, which is the continuous lines. And then we actually developed some manually vectorized code using LTVEC. Which basically is a wrapper for the 128-bit vector registers. And we see here that we no longer get this big difference between SMT settings, but still the best performance you can get at lower SMT settings. And it is actually, even though it is a compute-heavy benchmark, it's still very competitive with Intel numbers. And on the implicit case, which is these bottom ones, which does not vectorize very well. It's a very sequential operation. It's solving a tridiagonal set of equations using the Thomas algorithm. There it even outperforms the Intel machines because there it's really the clock rate that drives performance. Looking at another benchmark this time, this is a structured mesh partial differential equation solver. It's called Cloverleaf 3D. It's in the Mantivo suite. This is a primarily bandwidth limited application, and it consists of about 50 different finite difference like stencil computation loops. And here we also compare performance of pure MPI with MPI plus OpenMP. This is mostly in Fortran, actually. And we can see that, again, we get best performance around SMT2 or SMT4. And actually, we get a sustained bandwidth of, on average, of 160 gigabytes a second. Which is pretty good. On simpler kernels, we get 270. On more computationally complex and more latency-bound kernels, we only get 70 gigabytes a second, but on average, it's 160. And this is actually 1.5 times faster, almost, than a K40 GPU, let alone an Intel CPU. That's another factor of 2 there. So this is a very nice looking application. This is a structured mesh stencil computations. This actually vectorizes very well. So the IBM compilers went and vectorized, I think, about 90% of the computational loops in this application. The other example would be an unstructured mesh finite volume method application. Where computations are much more irregular. You no longer have that nice structured memory access patterns. The compiler can no longer really automatically vectorize any of this. But even then, we see fairly good performance, although more with MPI. With OpenMP, for some reason, performance just goes up, and it's significantly worse than just pure MPI. I mean, seeing a performance difference or performance improvement when going from MPI OpenMP to just pure MPI, we have seen on other platforms as well, not quite to this extent though. So again, we are a little slower than in the structured mesh applications, but still fairly good. And whereas the previous example was a very small application, we have also tested this on the production CFD application at Rolls-Royce called Hydra, which actually compiled almost without any changes, just tweaking a few compiler flags. And again, we ran similar tests, and we see that the POWER8 ended up being about 1.5x of what an Intel machine can do. But in this case, the GPU is a bit faster. This is a much more complicated application. And again, this is unstructured mesh, so it doesn't vectorize as well. So that's it about the benchmarks. The last thing I wanted to mention is IBM has put out this developer challenge where you can compete in 2 tracks, the Open Road Test and the Spark Rally. I guess you can read all the details in that link. So